are we going to start?
Okay, so welcome everyone. So today we'll have Siyang from USC to tell us about symplectic topology of hyperplane arrangements.
Yeah, thanks for the introduction. And well, if you're clicking, actually you cannot click on the screen, but if you're clicking like the archive paper, the title is slightly different with some very scary words. But the actual thing we do is actually about this kind of studying the symplectic topology of hyperplane arrangements, which is also our original motivation. And well, so in this talk, I will try to avoid those scary words and basically talk about anything, everything on this topology. Let's first introduce the background. What is a hyperplane arrangement? We usually use this notation V for a hyperplane arrangement, and we require it to be real. Which means that real means that it is real means that it is consisting of even hyperplanes in the real Euclidean vector space. And D is the dimension of this D is dimension plus one of these hyperplanes, and N is the number of hyperplanes. So one example, which I already draw here, ignoring the red line, this is like a simple example of hyperplane arrangement in dimension 2. And there are 3 hyperplanes. So if you ignore this red line, you will find that there are like just three black things which consisting of this hyperplane. You can also write in coordinates. The first one is, y equals 0. And this one is x equals to 0, and this one is x plus y equals 1. So what we want to study is not this hyperplane arrangement itself, because it is not a good symplectic object. The thing we are looking at is the so-called complexified complement of the hyperplane associated to a hyperplane arrangement. Well, by the way, this is a work with Cheuk, with Sukjoo Lee, and Cheuk is actually previously a PhD student in the University of Minnesota. So it has some relation with the university. Anyway, let's so what do we mean by complexified complement? So complexified complement means we take the complexification of these hyperplanes. So this is like a complexified hyperplane arrangement. Now not inside RD, but inside the C to the D complex vector space. And every affine hyperplane can be regarded as like given by some equation, which is linear function Li defined on RD and given by this equation Li equals 0, so that if we look at the hyperplanes, we use the same equation but now inside C to the D. So it will give us a complex hyperplane inside C to the D. Now it's like a complex hyperplane of codimension 1. And M of V is defined to be C to the D, removing the union of all these hyperplanes. This is the complement. You have these hyperplanes, but unfortunately you need to remove that. And when you remove that, you get something like with a very interesting topology. So in this case, we still use this picture to denote the complexified hyperplane arrangement. And here we look at the real part of this hyperplane. So in the real part, if you slice along this real part, you will still see like there are these three lines there, and now you regard them as punctures. You remove them. And of course, if you imagine this, you put this into C2, you will find that, well, let's look at a more even like even one-dimensional lower example where you have this line, which is R1 inside C, and you have these two puncture points because in dimension one, the hyperplane is really just a point. And now you see that the topology is not the same as C, because C has trivial symplectic topology, but now you remove 2 points, now it becomes a hyperplanes. So you see that like if you remove more and more hyperplanes, the topology becomes more and more complicated. And in one dimension, it's very clear that you are attaching some handles to this, to like a trivial to like a C. So you can see that we can see that this C is like lying inside somewhere. Like say you have a disk here. This is your C, and then you attach. Sorry, this is not parapents. I made a mistake. This is parapents, right? And then you attach two handles to the C so that you finally get this parapents. So the main goal of our paper and this talk is to study the symplectic handle structure of complexified hyperplane arrangements. Before I move into this point, I should state our main theorem, which is collaboration with Sukjoo Lee, Ying Li, and Cheuk, where here I should say some scary words. So we say the Fukaya Saito category. You don't really know what you don't really need to know what this is of MV together with a polarization is generated by bounded regions in the real part of MV. And moreover, if we label this real part by L alpha, where alpha belongs to P, is the index set of bounded regions of these bounded regions. Well, I should also tell you what is a bounded region. And here every time I introduce this theorem, I forgot this condition that we consisting only of transversely intersect hyperplanes. Transversely intersect. Well, basically, we don't allow in dimension 2, we don't allow this kind of configuration. But I don't know how to like . But if you have something which is parallel, this is completely fine. So, and moreover, we can compute the Fourier cohomology of the direct sum of this bounded Lagrangians, and it is actually formal, which means and the differential is actually 0, and all the higher A infinity structures are all 0, and as an algebra, so this is only algebra. And as an algebra, it is equal to something called the B algebra associated to this hyperplane arrangement with polarization to C. This is the statement of our theorem, but we can basically ignore the computation of the Fourier cohomology part if if no one wants to see how it's computed. And we can also think of Fukasado category as like you can replace it by the cohomology. This is really saying something about the handle structure of the space, but modulo some caveat that there are some additional handles that cannot be topologically cancelled but can be algebraically cancelled. And what are boundary regions? So polarization is just a choice of direction, which means it's like Gaussian. It's a linear function from Rd to R, which of course you can lift to like to the complex vector spaces where your Gaussian is has real coefficient. And we require to be general position, which means the level sets of Gaussian cannot be parallel to any of the hyperplanes. So in this case, you can see this is one choice of the polarization, where it gives you a direction that you go in this way, the value of the Gaussian is increasing, and the bounded regions are bounded with respect to this choice of polarization data, so that you directly see, like you just move your level set down, and you directly see that this one is bounded, and the lower one is also bounded, and this one is bounded. So in this case, we have these three Lagrangians. Yeah, question.
Sorry, I wanted to ask, like, how is this a two-dimensional pair of pants? Maybe there's something simple I'm missing.
Right. I wrote this two-dimensional pair of pants because if you look at this C2, remove the three hyperplanes. This one is the general. This one, if you, well, I try to think about a way to explain why this is a pair of hands, but so we call this one the generalization, the high dimensional pair of hands, or like so this is the two-dimensional pair. This is the two-dimensional pair of hands, by almost by definition. So in general, let's say in general, the higher dimensional pair of hands is C star to the n, removing a generic hyperplane which is transversal to all the coordinate axes. Or the standard one is just x1 plus xn equals 1, plus 1 equals 0. Is the n-dimensional pair of hands. Complex. The reason we call this is due to the work of Hawking, where he proved that if you are given any complex hypersurface inside C sub to the n, you can find a decomposition where each piece is exactly isomorphic to one such object.
Okay. Maybe one last question on this. Thank you,
Yeah.
by the way. Why is it +1 instead of -1?
This is -1 actually. Sorry.
Oh, okay. I was like trying to make sure I understood the algebra.
Yeah. -1 is actually this one, right? But well, these two are actually isomorphic. If you just look at the complex structure. So we sometimes just don't distinguish between these things. Because in general, if you start with a start to the end and start with any hyperplanes, it will always gives you something isomorphic to n-dimensional complex parallel pens. You can try to write down some isomorphism from one to the other.
Okay.
Okay, if there are no more questions, then I will go to the next part. So Weinstein manifolds. Why I'm talking about this? Because it is well, symplectically, Weinstein there are not all symplectic manifolds have handle structures. And we call those which admits a handle decomposition, which actually has a handle decomposition, Weinstein manifolds. So Weinstein manifolds are symplectic manifolds that admits a handle decomposition. This is basically originally due to Weinstein, who observed this fact. So we call such manifolds Weinstein manifolds. Decomposition. But there is a beautiful fact due to Chilibek and Eliashberg, where you can actually identify this with Stein manifolds, but just forgot about the complex structure. Well, if you are more familiar with this Stein language, then when we are saying Weinstein manifolds, we are basically talking about Stein manifolds. So of course, this complexified complement of hyperplane arrangements is a Weinstein manifold. If you just think about it and you embed this into some higher dimensional projective variety, you the pullback of the corresponding Fubini study metric or like the Taylor potential actually gives you this Weinstein structure, where the handle structure actually comes from pullback of the Taylor potential. Regarded as a Morse function. So at least we are able to understand the basic example of this, which is you only have n hyperplanes inside dimension. You only have d hyperplanes in dimension d intersect transversely, and they intersect at a single point, which is just C star to the D, or equivalently cotangent bundle of the D-dimensional real torus. And in this case, it has a symplectic handle structure which exactly coincides with the smooth handle structure on the zero section. So like coming from lifting of smooth handle structures from the torus. And we know that another fact due to triggered by Eliashberg is that the essential symplectic information comes from the top dimensional handles. And in this case, the top index handle, if you well, look at this unstable manifold, it is just a single cotangent fiber. This is the unstable manifold. Of the critical points. And it is always a disk because they will just go to infinity. Like it is like you start with a disk and then near infinity there are no more critical points, so you just freely flow along your gradient vector field, and then you get a cotangent and then you get a single cotangent fiber. So this our computation is is just based on this simple fact. However, I'm not saying that this easily follows from this, because if you try to imagine you remove another hyperplane, then trying to figure out like how many handles you need to attach to this is kind of messy. But there is a pathway in this kind of examples to do this. And we will introduce a slightly different approach to from our paper. A slightly different approach is due to the recent joint work in progress with another group of people. So this is actually a joint work with, well, let's talk about this. Let's first talk about what this is. So we consider a family of Weinstein manifolds. Ws, where S belongs to delta, where S belongs to C, which is still just a one parameter family of Weinstein manifolds, and such that well, this can be written actually as like a big map from W to C. And the restriction of this removing the preimage of zero is a symplectic vibration. And we want to preserve the handle structure so that we say that this is a Weinstein vibration over C star. So the only possibly problematic part is at the preimage of zero. and pi inverse of 0 is smooth, or say pi has no critical points. This may seem weird because usually we think about things in a complex setting and then there should be critical points. Otherwise, your thing is completely smooth, like you don't have any degenerations. But here the point is that Weinstein manifold is not compact. If you look at Stein manifolds, they are always non-compact, and the degeneration can happen at infinity. So there might be some interesting degenerations happening, but you don't see any critical points of the map. And under this setting, the result we are proving, which is joint work with Sheel and Wenyuan and Peng, is the following. So there are actually two such results, but let's just say, like, in this case, under the assumption the topology of the family is completely determined. So W is obtained from the product W0, which is pi inverse of 0, cross a disk by attaching a mapping cylinder. We call the symplectic mapping cylinder of a Weinstein cobordism so that all the well, I should say that top index handles are called co-course in the standard language of are called co-course of the symplectic manifold. So all co-course of W comes from vanishing symbols. And what do you mean by vanishing symbol? Well, if you draw the disk, which is the image of pi, you have this 0, which has something, but there are something happening at infinity, and you draw a line through it. So if you start with an L inside the cobordism, WT removing W0, and then you take a parallel transport of L along blue line. This gives you a Lagrangian which we call the vanishing symbol. And this Lagrangian is actually diverges to infinity as we approach 0. So these are called the vanishing symbols, and our result just saying that. Sorry, I should say this is not the paper, but in preparation. So that we can understand the symplectic topology of all such families by looking at these vanishing symbols. But this is just a local picture. So what do we mean by local? Well, globally, we can try to cut along so globally we can try to say like the critical points these are not critical points. These values, which we call atypical values, where the degeneration happens. And in general, you may have a lot of such atypical values, and you write them in a line, and then you can try to say I cut them into these pieces, and each one is local, so that you can understand the topology there, and then you try to glue all of these pieces back. Then for each such atypical value, you get a bunch of vanishing symbols, and then you just group them together, and then you get a huge collection of vanishing symbols, which describes the symplectic topology. But how do we cut? It is actually not like a casual cut. We need to use this so-called sectorial decomposition. So what that is? Well, this comes from the famous work of my advisor Sheel and Harden, and we've extended exactly in their second paper, which has an even fancier title, Sectorial Descent for the replica categories. So what is that? Well, so there is a version of Weinstein manifolds with boundary, which we call Weinstein sectors. There is a definition of Weinstein sector, which is like which you can basically regard it as like a pair x comma h, where h is a Weinstein hypersurface in X. Well, Weinstein hypersurface means all the data you need for defining a Weinstein manifold restricts to a Weinstein, to all the data you need to restricts to like a Weinstein structure on H. And this gives you some manifold with boundary. Which looks like X removing H cross a copy of R. Then this gives you like X remove H cross some half space, and then you see this is codimension 0, so that you get a manifold which is maybe we called Y, where we call W with boundary diffeomorphically identified with H cross R. With a prescribed Cover neighborhood given by H cross R, and then you cross another copy of minus epsilon comma 0, and this forms a symplectic subspace. And this is a symplectic. The symplectic form is restricted to a symplectic form on this product, like something like this, a color neighborhood. And what is the good thing for this? Well, we can try to write down a handle structure which is relative to the boundary, and is suitable for gluing. Oh, sorry. Suitable for gluing, which is well, you have this like a Morse function, which we say like a coming from a Taylor potential, and we require that F restricted to like a neighborhood of this is of the form the standard Weinstein structure on H plus like a Morse function on H, and then you plus some standard like 1/2 of R squared, where R is the radial direction, where R is just like if this is x and this is y, it's like a x squared plus y squared, taking the square root. So you can imagine that you have a product of H with some disk, and you set your symplectic structure to be it's not of this form. Let me think. I think it should be going inside and outside. So it's like 1/2 of x squared minus y squared, so that it has an index 1. Right. So you can imagine you consider a disk of this form where it goes inside this way, and then you go outside that way. Like this is C. But you cut along the middle line so that you only look at the left-hand side. And if you have another boundary where it looks like the same picture, then you can just glue along the middle. Right? So then we can glue 2 sectors along H cross R. And this is suited, and the one-thing structure on both sides will coincide near the boundary so that you get a well-defined smooth function on the glued space, which gives you like which provides you such pattern for like going from local handle structure to a global handle structure, with the caveat that you need to introduce a handle structure here. So previously you have like a co-core which so previously like the core goes this way, like it is a disk but you cut in half, so it's a half disk. And now when you glue that, you find an honest handle there, which is a core. Core is just like a stable manifold. You get an only stable manifold in this way, and then it gives you some handle structure which cannot be a priori removed. So you need to put it there. But this introduces additional handle structure coming from that of H. So this is regardless of this caveat, we actually obtained like a very good pattern for how to glue local things together, and this is almost the proof of how the proof of the generation modulo some Lagrangian surgery formula. So about the proof is like this. If we regard C as like if we regard C as like a Weinstein hypersurface, how to regard this as Weinstein hypersurface? Well, you look at the preimage of C at a single value, which is the real value for M sufficiently large. Then this gives you a hypersurface there, and you can show that after deforming the symplectic structure, you get the real part. Like if you look at the real hypersurface defined by C, this gives you the almost gives you the product structure. So you see that it gives you like if you cut along this, it gives you a Weinstein sector, and you can do this when you pass through every single point. So this is like a H1, H2, H3. And when you have these 3 real hypersurfaces, you can just cut it along this line so that you get like a 1 sector, 2 sector, and 3 sectors. And there is potentially a 4th sector, but this is a product, but this is a trivial sector. Trivial means that it does not have any co-cores except from those coming from the boundary. So and how should we think about these three sectors? Let me go back. So M of V can be regarded as the union. So let's say let's remove the real Kersey inverse from M to power to infinity. If we remove this, it consists of x1 union x2 union x3 along the same real hypersurfaces, and each xi admits a map over C to cotangent bundle of an interval, or to see where the real part of Z belongs to a certain range. So this is a strip. And there is a special point where your Kersey inverse of this Ci intersect with the hyperplanes, which are intersect with all the hyperplanes. Or I say it does not intersect transversely with hyperplanes. This actually gives us the degeneration. If you imagine I'm moving this hyperplane upstairs, and each part you just get a two puncture plane. And when you go into this intersection, your two puncture plane becomes a one puncture plane. So this is C2 remove 2 points. And if you go through this point, what you get is like a C2 remove 1 point. Sorry, C, which is a C star. And how to compute this vanishing symbol? Well, you look at those Lagrangians which diverge to infinity via this under this moving. So you will see that this is the vanishing cycle. This gives you the vanishing cycle. And you flow along some line so that you get this beautiful vanishing cycle in this way. So this gives you a vanishing cycle which looks like this. And now we glue all of this. We will glue all of the things together. So we glue back x1, x2, and x3. And when we glue back, what we get is like for each crossing point, if you think about this, for each crossing point, I get a symbol. So there are 3 crossing points, which means I get 3 symbols. One is here, and the other is here. Actually, we need to pass through this, and then we actually need to also pass through the Lagrangian is not allowed to touch the boundary, so that it should go to infinity. And then when you glue back, your Lagrangian is still there, and if you try to wrap it down, you obtain a Lagrangian which is asymptotic to these two very long hyperplanes. The Lagrangian is actually the whole cogent of this point. And similarly for the upper one, you should get this like a whole triangle, going to infinity. So these are very huge objects. So they are not bounded chambers. They are not bounded regions. But you can see that if you draw the things this way, it looks like a direct sum of them, or a sum of them. But a sum of them. So if you want to try to do this like if you want to run this handle story in this case, you will find that if you introduce this this sectorial cut, each boundary gives you a non-trivial handle structure, which you also need to handle. But the good thing is that if we work algebraically using this fancy word, we can actually show that by Lagrangian surgery, due to the work of Cheuk and Wenyuan. Possibly almost everyone here know this famous work. You can see that the vanishing thimble can be written as a direct sum of bounded Lagrangian regions. For some, it's direct sum of certain bounded Lagrangian regions. Depending on how you flow this down. And still, you using the same work, we can also show that handles coming from boundaries can be removed as well. Via surgery. So if you want to study the whole generation, if you want to study the whole topology by writing down all the handles, then you cannot do this because this does not say that topologically the handle can be removed. If you want to show the handle can be removed, you need to find the canceling pair and then you cancel them. That is much harder than doing things algebraically. But if you work with categories, they cancel due to the surgery formula. And that is the reason why we work with this work with this categories instead of working with the topology directly. So this basically finishes the discussion of the generation. And yeah, I can also briefly talk about the computation of the four cohomologies. But before that, any questions? Okay.
So can you go back to the statement of the
Yeah.
So you show the computation of the the Floer homology.
Right. Yeah.
So,
Well, actually, I don't tell you what this algebra is, but the algebra is almost like if you know how to compute it, then it matches automatically. Yeah.
So what's the meaning of putting a psi under W?
Sorry.
So what's the meaning of putting the polarization of psi under the wrap for complexified?
Oh, so if you look at this like Lagrangians, say, let me find a way. So let me draw a line here. So like say like I have this. Let's look at one-dimensional examples. This is C, remove 2 points. And you pick a bounded Lagrangian so that your cassette can only choose to be left or right. Say let's do this left. Then you have these two Lagrangians. L1, L2. And you want to compute the flow cohomology from L1 to L2 or from L2 to L1. And wrapped means that, well, your cassette is here, so that you put a point here, and then when you there are actually three directions of infinity, where the 2 comes from here, and there is a mysterious one which is infinity. So these 2 are removed, so that you should really regard it as like an infinity instead of some finite point. Then there are some wrappings. Well, wrappings are like you consider rotating Lagrangians near infinity. The infinity is like a divisor or like a single point in this case, so that it has a circle bundle around this, which allows you to do the rotation. Like so let's say like L2 is like, don't use this curved. And what you do is you try to perform a rotation near the point, and then previously they don't have intersections, but after you do this rotation once, you have an intersection point. And of course, you can do more times. Like you can rotate this twice. Then you get 2 intersection points with L1. If you don't rotate L1. So you can imagine I rotate this infinity many times, and then you have an infinite intersection with L1. So you a priori get an infinite collection of generators. A priori, you get a CW star of L1 and L2. Well, it should be L2 and L1 because I'm rotating L2 which intersect with L1. It is like an infinite collection of xi, where I is like, it is over z of xi, where I is greater than or equal to 1 or 0. Well, maybe, let's say 1 as just as a vector space, or like as a module over z. And in this case, you can directly see that there are no differentials. There are no disks in this one-dimensional picture. If you want to find a disk, you need to find the embedded polygon inside this Riemann surface. But if you draw the picture, you cannot find any. And here it has a it has a multiplication where your x1 times x1 should be x1, it should be x2, and x1 times x2 should be x3, and so on. Sorry, there are no computation. So there is a module structure where you have an action of L1, L1, and here you have a L2, L2 acting on this. And this action is like, if you have this L1, L1, it's actually given by 2 generators. Let's say x, y, coming from these 2 punctures. You can rotate here, you can rotate here. And they have no relations. So x times y should be 0. Sorry. There are no relations. X times y is not 0, so it's just freely generated by this polynomial ring. And here, you have a puncture here, but you don't have rotations at infinity. If you want to rotate, you attach, you have intersection with this red line. Or red line is really just like a whole real part. So that whenever you try to do this rotation, at some point you intersect with this red wall, which is not allowed. So that you only have one generator, which is a single polynomial ring.
So Kasai is like telling you each part is not the significant end where you cannot see the line.
Sorry?
The Kasai, the function of Kasai is like telling you where is the cylindrical end.
Right, it tells you where the wrapping is obstructed.
Okay.
Like if you remove this C, you can still write down the algebra. Like you just add like extra directions to all those which actually diverges to infinity, not diverges to these punctures. If you regard them as different, say different like if you treat with them differently instead of like regarding them as the same. So well, and why can we show that all like there does not exist any like a mu3, mu4 like this higher A infinity structure? This is based on the fact that X is like a 1, 0 graded and Y is 0, 1 graded. You can introduce to each puncture like a hypersurface grading. And the gradient just counts like how many times you wrap around this, you rotate around this hyperplane. And then this makes your whole algebra multigraded. And if you just keep track of like what the infinity structures how the infinity structures change the grading, you will find that only mu2 is allowed. There are all the other things are not allowed. Like the gradient would contradict if you introduce this multi-grading. So that tells you that mu d is non-zero only when d is 0, only when d is 2. And when d is 2, this computation it actually reduces locally to each hyperplane. Where to near each hyperplane you just see something like this. And your Lagrangian is here, and you try to wrap around, or another Lagrangian is here. If you cannot find such hyperplane, you don't have any like say if you don't have such hyperplane, then you just cannot find any elements. Which means also which also means like the composition is also 0. So this very roughly tells you how to compute this algebra, and the conclusion of this algebra is like this. So given alpha beta, if alpha and beta are relating by a hyperplane, otherwise it's 0. The Fourier cohomology of L alpha, L beta is given by, you start with the polynomial ring with all this like indexed by all these hyperplanes, and it's multigraded, and you divide it by the relation, well, let's say U, divided by the relation US, where S is a subindex set, and all the relations such that the intersection of all these I inside X, I belongs to S of the hyperplane, intersect with the closure of L alpha and closure of L beta is empty. So you have these two regions, and then you only look at all the hyperplanes with non-trivial intersection along this blue line. If the intersection is empty, you remove that, and you also need to multiply by an element which we call f of alpha beta, which is given by this wrapping halfly from alpha to beta, and then you have an intersection. So this is a module. And if they are the same, then you just get this algebra. And you multiply by the idempotent. This is just as idempotent. Like if you want to direct sum, if you want to take the direct sum of all this like L alpha L beta, like over like all the alphas and also all the alpha betas, then it has a idempotent decomposition where the sum over all this E alpha alpha will become 1. It is like a product ring decomposition. So this is finally what the algebra looks like. Of course, you don't need to use any floor theory to write down this algebra. It's purely combinatorial. Okay, so I will probably end here, and thanks for listening.
Oh, so thanks, yeah.